Hey, what's going on everyone? Welcome back to Structure Free. And in this video what we're going to do is calculate the moment of inertia about the horizontal axis for this channel cross section. In order for us to do that, the first thing that we have to do is calculate the geometric centroid using first moment of area calculations, and then we'll use the parallel axis theorem to calculate the second moment of area, which is also called the moment of inertia or resistance to rotation. Now the first thing I like to do is look for any planes or lines of symmetry, and I see from this cross section here I see a vertical line of symmetry, and I don't see a horizontal line of symmetry, but I do know that my geometric centroid will be somewhere along this vertical line of symmetry, and because my area, I have more area to one side of the cross section, I know that my centroid is going to be somewhere closer to where there's more area. So here, this is probably somewhere around here is going to be my geometric centroid. Now the next thing that we're supposed to do is select a datum or a reference to calculate or locate the geometric centroid. And what we're really trying to do here is, or what we're really doing is picking a reference point, an origin, a point from which we're going to describe all our distances. And I can make that point anywhere, and I'm going to choose for this case, for this problem, I'm just going to choose this corner, this left-hand corner here, and I'm going to have a horizontal datum here and a vertical datum here. Yes. And once I have my reference or my origin defined and my datum lines, I can define where, or I can define values or variables to locate my centroidal distances, right? So here, this horizontal distance from the vertical datum, this would represent x bar, and this vertical distance from my horizontal datum would represent y bar, or my centroid in the vertical direction. From symmetry, we know that x bar is equal to 100 millimeters, which is half the distance, this 200 right here, right? Smack dab in the middle. Now the next thing we want to do is apply the first moment of area relationships to calculate this y bar. And what I mean by that is this y bar, this equation that you're all probably familiar with, is the sum of ai times yi over sum of ai. And this works for composite shapes. When we say composite shape, that means like something you can break up into rectangles, squares, triangles, circles, things that have like known moments of inertia about its own axis, or they're easy areas to calculate. Otherwise, you'd have to bust out some integral and do all that fancy schmancy stuff. But hopefully, most of the times, you're not going to be designing, some funky cross-sectional shape for your beam. So in order for us to apply this equation, what we got to do is break up this channel shape into manageable areas. And so for me, the first thing we want to do is, and so I'm gonna do that down here, and the reason I'm gonna do that down here is because I'm gonna create a table. But here I have the same cross section again, same drawing as before, and what I'm gonna do is, let's see, I'm just gonna break this up into 3 rectangles. So I'm gonna draw a line here and a line here. So I have area 1, 2, and 3. And I want to make a table that kind of matches this relationship here. And let's see, I numbered each of my areas, and I have 3 of those areas. So I'm going to draw a line for each area, or each section. I broke it up into here. So this will be number 1, number 2, number 3. And the first column, I'm going to calculate the area of each of those, and this will have units of millimeters squared. The second one, I'm going to calculate this yi is the distance, or the vertical distance from the datum, or in this case this horizontal datum, to the centroid of each of the manageable areas. This last column is going to be the multiplication of ai times yi, which will have units of millimeter cubed. My recommendation is to always make a table until you get really, really proficient at doing these calculations on a single line or whatever. Alright, but just for now, keep doing the table until you get good at it. So let's go ahead and calculate the areas. So the first area here is this area 1. Bam. And shoot, I got colors. Let's use some colors. For area 2, let me use yellow. Oh, can you even see that? I don't know. And then area 3, I will also use green again because it's the same as area 1. And so if I calculate the area of each, area 1 is base times height, so 20 times 150. This comes out to 3,000 millimeters squared. Now I know area 3 has the same dimension, so this is also 3,000 millimeters squared. Area 2 in the middle here is a base of 160 times the height of 20, which gives me an area of 3,200 millimeters squared. Now the distance from this reference, the horizontal reference or the datum, to the centroid of each, so area 1, the centroid is right about here, so this would be, this distance will represent y1, as would right here, this would be y3, and then the center of this would be y2. And so that's pretty simple. So y1 is just straight up 1/2 of 150. That's 75 millimeters. And y3 is also 75 millimeters. The centroid of area 2 from the reference is, let's see, this is 150. This is 20 millimeters. So 150 minus 20 divided by 2. And that will give me 140 millimeters. Now we just go across the table, multiply a times y. Boom. So this will be up 225,000 millimeters cubed. And then for area 2, this AI times YI is 448,000 millimeters cubed. And now to solve for this y bar, all I got to do is, fulfill this equation up here. And this summation up here, this is going to be the summation of this column. If I sum up each of these values, this summation value is 898,000 millimeters cubed. And this represents sum of AI, YI. Yes. Here, the sum of the areas is the sum of each of these three values. And that is 9,200 millimeters squared. Now if I straight up plug and chug y bar is equal to 97.61 millimeters. And my centroid is located 100 millimeters horizontally from the reference and 97.61 millimeters vertically from this origin right here. Yes.